Dr. Weiss, please take it away.
Thank you, Scott, and good morning from a very sunny, bright Worcester, Ohio. Today's webinar is on minerals, and obviously minerals is a broad topic, so I had to be quite selective on what I'm going to talk about. So I'm not going to address every mineral, but I want to talk about some principles and some application, but I will not get into every single mineral. Okay. No matter which software you use to formulate, the mineral component is almost sure for certain NRC based. These different models may have different amino acid models, different energy models, but the mineral equations are pretty much right out of NRC. And the basic concept from 2001 NRC was the requirement for a mineral, for a given mineral, was basically what to meet this in the blue box here, and that was to feed enough absorbable mineral to maintain body stores, body fluid concentrations, and allow the cow to do what we want it to do. So to do that, we lose every day a cow is going to excrete a certain amount of absorbed mineral via feces, a little bit via urine. That's a pretty small loss for most minerals, but this is mineral that was absorbed and now is being sloughed or lost in secretions. And so the cow has to replace that, or body stores drop. Minerals are in milk, so we have to replace the minerals lost in milk every day. If the animal is growing, then this isn't really lost, but this mineral has to be deposited into new tissue to maintain body stores. And then lastly, if the cow is pregnant, she's accreting mineral in the fetus and fluids, those have to be replaced. So we have to meet all these needs without losing body stores. Otherwise, we are not meeting the requirement. When we break this down, these three here, milk, growth, and fetus, we have decent data on the concentrations on that. It's not, especially the fetus is kind of old data, but it's reasonable data. So the requirements for these, I think, are pretty good. Maintenance, though, which is feces, inevitable loss in feces and urine, is very difficult to measure, and that's I'm going to talk a bit about that as well. So this requirement here is probably the least well known, or the one we have the least amount of confidence in. And for some minerals, it's the biggest single requirement. So we have some issues here on requirements. We also have to maintain adequate stores. I can have a deficient animal feed enough minerals to do all these things, but she's still deficient. So we have to know when an animal is adequate. We have to feed enough mineral to get up to adequate status and then maintain that. For some minerals, we know what is adequate. We have markers for adequacy. Other ones, we really don't. And then the last part of this is absorbed, and that's what most of this talk is going to be about. This is not an easy thing to measure. Absorption coefficients for most minerals are exceedingly difficult to get. Okay. Another issue with factorial, and I should mention, if you have the handout, I hit a few slides, so just move ahead. I didn't change the order. But in theory, if the requirement we produce is the mean. That we take a bunch of different experiments, come up with equations from these different experiments, and we're generating a requirement for the mean animal of a certain animal, of certain body weight, certain milk. And with the mean, that means half the cows are fed adequately or excess, half the cows are not fed enough. If we feed strictly to the mean, NRC is the mean. That's their job, is to do the mean. If you look at the human system, or the US system for humans, you see they don't call it a requirement. They call it an RDA, a recommended daily allowance. And what the RDA is, it's the average requirement plus 2 standard deviations. And so the RDA for the human system, its goal is to feed essentially 100% of the population. And statistically, it's a little more than 97%. So for animal nutrition, we got to do something similar. We don't want to feed just the mean, we want to feed a bigger proportion of the population. The big problem with this approach, though, is you need a standard deviation on the requirement. And for humans, for most minerals, they have no idea what the variance is. And so what they do is they use the same standard deviation they get for energy metabolism. And that's the CV for energy metabolism for a specific human population is about 20%. And so the RDA for most minerals and vitamins is the mean times 1.2, 20% extra. And I think that's a very reasonable safety factor for minerals for animals as well. 10 to 20% above what NRC. And it's not, I don't consider that overfeeding. It's overfeeding an individual, but it's not overfeeding the population. It's feeding most of the population correctly. But it's only 10 or 20%. It's not 100%, which I see too often. So feed excess of about 1.2 times NRC. The other thing I always want to remind people of is most nutritionists are more than willing to feed more than requirement. And as I just said, they should. But people forget on the other end of these things, everything is toxic in excess. And for minerals, we start seeing negative signs, or at the point we start seeing negative things, we call that the maximum tolerable level. It could be as little as reduced intake and reduced milk, or it could be something major like a very serious illness or disease. This also has uncertainty. So if you're going to add 20% to this, maybe you ought to subtract 20% from the MTL. So for example, copper has an MTL of about 40 parts per million. You know, you want most animals to be safe. So maybe you ought to reduce that by and say, I don't want to feed anything more than 30 or 35 parts per million copper. So just be aware the MTL is also a mean, and so stay away from it. Don't go right up to the edge. All right, what we're going to talk about mostly is absorption. So the basic system is we measure the mineral in the diet, we apply absorption coefficients, and we get grams or milligrams of absorbed mineral that are available for use of the animal. For most minerals, commercial labs can measure feedstuffs quite accurately. There's iodine is more difficult to measure, selenium is more difficult to measure, but most minerals we have good lab assays. But we have constants. These are the absorption coefficients are almost all constants, which we know isn't the way it is, but that's the data we have. So how do we get these things? I want to spend just a little bit of time on the methodology so you appreciate just how difficult it is to get these numbers. One is we could do just mass balance, and that means we measure how much is eaten, how much mineral is eaten. We can measure how much is in fecal to get apparent absorption, shown down here, just intake minus fecal. We can get apparent balance by also subtracting out milk and also subtracting out urine. This apparent absorption is not the availability coefficient. Too many people think that's all you have to do. And you can't do it. Just collecting fecal samples or fecal output and subtracting intake does not yield absorption coefficient. And the problem is in the feces, there is unabsorbed dietary mineral. That's the number we really want. How much of the mineral that you fed was truly not absorbed by the cow? But in fecal samples, we also have this stuff called endogenous fecal mineral. This can be sloughed intestinal cells. It can be some fluid secretions. It could be some enzymes, but it's stuff it's minerals that were absorbed once and now are being excreted. We have another fraction, what I call is homeostatic excretion. Some minerals for cows to maintain, when you feed excess minerals, for them to maintain the proper amounts in their body, they dump excess, they absorb it, but then they dump excess out in feces. Some minerals are excreted excess in urine, some in feces. Manganese, some of the trace minerals go out in feces. So what we really, to get the true availability, which is the absorption coefficient, it's intake minus feces, but then, or fecal mineral, but then we also have to get rid of metabolic fecal mineral and this homeostatic fecal mineral. These are not easy to measure. They're extremely difficult to measure. The other thing here is we want to measure true availability when cows are fed at about the requirement. Some minerals, the absorption is regulated. And so if I feed a lot of extra minerals, the absorption coefficient would be low because the cow downregulates absorption sites and it's simply not absorbed. It's available to the cow, but the cow just doesn't need it and won't absorb it. So we have to measure these at what we think is about the requirement to get accurate measures of availability coefficients. Now, for some minerals, we can actually use fecal excretion almost exclusively. And this is an example with potassium. This is called a Lucas plot. It's been around for a very long time. It's used for a lot of nutrients. And what we do is we plot the intake or concentration, but the intake of in this example, it's potassium, versus the intake of the absorbed calcium. Absorbed potassium, I'll get it right here. So it's what they ate versus what they ate minus what goes out in feces. No adjustments, just total fecal loss. And we plot these two, and if for some minerals, we get a nice straight line, good fit. And for this plot to work, the intercept, the intercept has to be negative or 0, but it cannot be positive. And the slope has to be equal to or less than 1, statistically equal to or less than 1. The slope is the absorption coefficient. And what this is saying is potassium is absorbed with 100% efficiency. The absorption coefficient is 100%, because this is not statistically different from 1. The intercept is the endogenous fecal loss. So this is saying these cows lose 2.5 grams of potassium for every kilogram of intake. So this would be the fecal maintenance requirement. This is the absorption coefficient. And it works well for electrolytes. This method works well for electrolytes. A point I want to make here is with the old NRC, endogenous fecal for almost every mineral was a function of body weight. And that's incorrect. It should not be a function of body weight. It should be a function of dry matter intake. And you're going to say, well, does that really matter? And it matters a lot. You can have a dry cow and a lactating cow that weigh the same. With the old system, they'd all have the same maintenance requirement for minerals. That's not correct. A lactating cow is going to eat 2 or 3 times more than a dry cow. Her endogenous fecal loss should be 2 or 3 times what a dry cow is. So one thing we need to do is switch on our requirement end is switch endogenous fecal or maintenance to make it a function of intake. And that should help us quite a bit on comparing dry cows and lactating cows. Okay, this approach here, as I mentioned, works for the strong ions. You can read this yourself, but potassium, sodium, and chloride. This is the method we should use to get absorption coefficients and metabolic fecal requirement. We can also use it with magnesium, but there's some adjustments for magnesium. It's because of different sources and antagonists, but we can use it for magnesium. A way to measure endogenous fecal losses is the standard way is using isotopes. We feed stable or radioactive isotopes of the minerals, and then we measure excretion in the feces. The isotopes come from the endogenous, and the non-labeled is diet. It works very good. This is how we determine it for humans. It's very expensive. And for cows, it's very, very expensive because they're so big. If we use radioactive isotopes, which is almost impossible to use now, we have the waste problem. And because of this difficulty, most of the, especially the trace minerals, most of the absorption coefficients are 50, 60 years old. They were determined back when they could feed radioactive manganese and radioactive calcium. We can't do that now. So just be aware these absorption coefficients we use are quite old. Some of them are quite old. Okay, on macros, the ACs I think are getting quite good on average. We've gotten more data. We've got better ways to analyze the old data. A couple issues here from NRC 2001. They gave a calcium chloride an absorption coefficient of 95%. That was based on calf data. Calves are better absorbers of minerals than ruminants, functioning ruminants. If you look at the data for older cattle, it's only about 60%. And you're going to say, well, that's just one feed. What's the big deal? Well, the problem is for a lot of these minerals, we will have an absorption coefficient for one or two sources, and everything is relative to that one or two source. And calcium chloride was one of those reference sources. So that means a lot of minerals, a lot of sources of calcium were overestimated. The absorption was overestimated for almost all calcium sources. Also, when we start using EF, is endogenous fecal. But when we start applying endogenous fecal as a function of intake rather than body weight, we get more accurate estimates, and the old NRC requirement was too high. So some of this error will cancel out. We overestimated absorption, we overestimated maintenance requirement. So even if we correct for absorption coefficient, it's not going to have a huge effect on the average diet. It's going to have effects on certain diets, but not on the average diet. Phosphorus, the old NRC gave feeds, not supplements, but feeds absorption coefficients of I think 64 and 70%. 70% for concentrates, 60 or 64 for forages. There's been a lot of work on phosphorus, and one thing we can do is partition phosphorus into inorganic and organic. These have different absorption coefficients, so you could send a feed in, it gets assayed for organic and inorganic, and we can just apply math here. See, grass hay with 2/3 or inorganic, 1/3 organic would have an absorption coefficient of 79. Bean meal would have an absorption coefficient of 69. So with this system, we're now starting to make absorption coefficients not constants. We're putting variation into them like we know they have. Magnesium. It's a tricky one because there's so many antagonists. For most macro minerals, antagonists aren't an issue except for magnesium. There's a linear effect or linear antagonist of potassium. You feed more K, cows absorb less magnesium. Linear function. Long chain fatty acids. We don't know how this relates, whether it's a linear or whatever, but if you're feeding a few percent added fat, I would feed 10 to 20% more magnesium to account for soap formation in the rumen. The endogenous fecal now as a percent or as a unit of intake is about 0.3 milligrams per kilogram DMI. And this is a good number. So we can use this to come up with ACs by using apparent absorption. These are two studies here. One we did a long time ago, and this one's out of Europe. It just shows the linear relationship or the linear antagonism of dietary potassium versus magnesium absorption. What you'll notice though is in our study, and this is actually a meta-analysis, we got a negative coefficient of 7.5 units of absorption for every 1% increase in K. The study here out of Europe only got a 3.1 unit decrease. And you're gonna say, well, my God, why are these so different? This was also a meta-analysis. This mostly dry cows, all lactating cows, so that might have some effect. But the biggest thing is the amount of magnesium in the diets. In the blue line here out of Europe, they fed very high magnesium. The average for those studies was 0.45. We only fed 0.25. So what this is saying is you can overcome this antagonism. You won't ever eliminate it, but you can reduce the antagonism by just feeding more and more magnesium. But we have equations. So you know the dietary K, you know the dietary magnesium, we can estimate absorption. This is more recent data from Alex Tebbe out of our lab, looking at the effects of Menensin. We fed high K, we wanted antagonism. We fed some high mag to counteract some of the antagonism. 2 sources of magnesium, good, very high quality mag ox or mag sulfate, with or without or 14 milligrams per kilogram dry matter Menensin. We did not balance for sulfur on purpose. So sulfur may be very much involved here. But if you just look over here at the scarlet bars, mag sulfate is more available than mag oxide, which we all knew. It's not that much more though. This is much less than people think. It is better without Menensin. When I feed Menensin with mag ox, absorption increased by more than 25%, huge increase. When I fed Menensin with mag sulfate, it decreased by 1/3. I think this involves the sulfur more than anything else. But on a practical basis, we don't feed mag sulfate to lactating cows, or you really shouldn't. There's no reason to. We do feed it to dry cows, and we do feed Menensin to dry cows. This is a lactation diet, so I want to be careful on extrapolation. But this is suggesting if you're feeding mag sulfate and Menensin to dry cows, you need to feed more magnesium to counteract this drop in absorption. So with all this new knowledge and different endogenous fecals and all that, we've come up with new absorption coefficients for magnesium. These are what was in NRC. You can see diet actually is substantially higher, twice as high. And I should mention these numbers here are all assuming 1.2% K in the diets. So I've corrected for K. This very huge variance here on absorption is because of K. So if you're worried about K, you might want to stick with this old NRC number, -1 standard deviation. But you'll notice here that the supplements are much, much lower than old NRC, much, much lower. You're going to say, why is that? Well, this is a mathematical thing. Remember, we can't feed magnesium-free diets. So if we underestimate the availability of the basal, then that error has to be corrected for. So this is really just because we use the wrong coefficient for diets. These, I think, are much more accurate. So mag ox, even good mag ox, is only 25% available. Mag sulfate is only 35% available. And I won't go into this a lot, but we're all aware of the high variation in mag ox quality. These are relative availabilities. And it went from, the best was given 100%, the worst was 10% of the best. So huge variation. This is old data, but I think this amount of variation likely still exists. There's still a lot of crappy mag ox out there. I get a lot of questions, is there lab test? And there's the vinegar test. I think that might be able to rank these. I don't know if it could separate the blue from the red or the green from the purple, but it could probably definitely separate the purple from the blue. But that's ranking. It cannot quantify. It cannot say this mag ox is 30% available or 20%. So it might be able, that lab test or that vinegar test might be able to throw out these really bad ones, but it's not going to be able to give you an absorption number. Okay, trace minerals. All I'm going to say here is it is extremely difficult, much more difficult to measure ACs for TMs because of lots of antagonism, lots of interactions, and regulated absorption. So these numbers are very, very, have a high degree of uncertainty. The other problem for trace minerals is these absorption coefficients are really low. Copper is somewhere between 3 and 5% available. And when you have a really small number in the denominator, a small error really adds up. And I just made an example here. I said we can have basal at 3% available or 5. We can have copper sulfate at 4 or 6. So I'm not changing these very much. If I assume high for basal, high for copper sulfate, I only need to feed, in this example, about 50 milligrams of copper sulfate a day to meet requirement. If I assume low and low, I have to feed 10 times as much. So these errors or these numbers are not very different. The errors are high. So just be aware that a small change in these absorption coefficients for trace minerals have a huge effect on diet formulation. The other issue here is all feeds right now in the NRC system, all basal feeds, feedstuffs, not supplements, have the same coefficient for all the trace minerals. Or the trace minerals would differ, but within a trace mineral, all feeds have the same absorption coefficient. We know that's not right. Here's corn silage. We know if you have corn silage with really high coppers, a lot of that copper is soil. Soil copper has almost no availability. So the absorption coefficient for this corn silage will be quite low, or it's low anyway, but really low compared to this number. And we don't have ways to quantify that. All I can tell you is that if you have feeds, and especially forages, with high ash, your absorption coefficients for your trace minerals are likely lower than what you expect. That's all I can tell you. I can't be any more accurate than that. Antagonists. This is a list of the four main trace minerals we're worried about. The ones in red here are known antagonists. If it's red in two different colors, it's maybe. So sulfur is a clear antagonist for every trace mineral, every single one. Iron is kind of an antagonist for copper and manganese, but I'm saying it's kind of because it has to be really, really high. And it's getting to the point where the diets we feed would not be that high. And also iron in forages is not very absorbable. It's almost inert, so it doesn't antagonize very much. You can see the other ones here. If on phosphorus, it's high phosphorus affects manganese, and it's by high the requirement actually antagonizes. If you feed the phosphorus to requirement, you are antagonizing manganese. So one reason we have to feed so much manganese is because we have to meet the phosphorus requirement. So just be aware of these things. If you have especially red ones, increase the amounts in your diets. Relative availability. That's what we can measure that. You might be able to get that number from companies, and it's just everything is relative though. We measure something for copper, it's liver, of the standard copper sulfate and of the product, and it's the ratio. But I want to emphasize the interactions here. This is with tribasic chloride. With antagonist, it was almost twice as good as copper sulfate. In deficient animals, they were the same. So you maybe with antagonist, you say this is good, higher availability, but in deficient animals, just feed copper. So be aware of all these interactions. Okay. Be aware of what you're measuring. If I use colostrum as my measurement, selenium yeast is twice as good, twice as available as selenite. If I use mastitis, this is the reduction, selenite and yeast are the same. They both reduce mastitis 10%. So be aware of the response factor. Okay, so what do you do if a company shows you data? My product has twice the bioavailability of copper sulfate. What do you do? With copper, I adjust for availability. So if their product is twice as high, I'm going to feed half as much. Selenium yeast, I don't make any adjustment. I feed the maximum legal amount. Manganese is so poorly absorbed, I don't think it matters. And zinc, I don't adjust. In other words, if I'm going to feed some organic zinc, I feed the same dietary concentration, total concentration, as I would with inorganic. And I'll explain why I do that in a little bit. This is just for your information. The ones in red, these are, to me, these are my best guesses on revised or ingredient absorption coefficients. The ones in red are notably different from old NRC. I didn't get into manganese. We can dig up more old data, and that's why the old one was about 2%, and now it's down to less than 1%. So this is just for your own information. So what would you do with those new coefficients? Well, if you're feeding a lot of supplemental magnesium, your diets are going to be higher in magnesium, because the availability of that magnesium is much worse than we thought. If you're feeding a lot of supplemental calcium, for example, corn silage-based diets, you're probably going to increase the calcium in your diets. Phosphorus, depending on inorganic and organic, and you're going to feed more, compared to the old NRC, you're going to feed substantially more manganese. Okay, organic trace minerals, are they more available? Well, I'm going to say, look at this study, and the answer is yes, for copper. Liver copper is a great indicator of status, and in this study, organic trace mineral is 1.5 times as available as the inorganic. If you're using liver zinc, which is not a good status indicator, but if you use it, you're going to assume inorganic and organic was the same, and the same for manganese. They may or may not be. It's just that liver manganese and liver zinc are not good status indicators. But this study says organic, at least this specific organic, was better. This study says just the opposite. This is liver copper, this is beef cattle. In this study, the inorganic was 25% better than the organic. And all I'm going to say is, don't make these blanket assumptions that organic is always better. It depends on the product, obviously. It depends on the diet. It depends on the mineral status of the cow. And you have all these interactions. So a certain organic trace mineral might be great in this condition or this situation, but not in another one. Just don't think everything's the same, because it's not. And this is a study Matt Faulkner did a couple years ago, again, showing interactions. This was hydroxy versus sulfate. In a forage-based diet, the hydroxy gave higher apparent copper absorption. Copper balance. But when we fed a ton of byproducts, we see just the opposite. The sulfate was superior. So again, it depends on the product. The value of a product depends on how you're feeding it. Do not assume everything is the same regardless of diets. And what I want to finish up on is this question: is absorption everything? Well, a mineral, if it's going to maintain body stores, obviously has to be absorbed. If it's going to go out and milk and feed us and so on, it has to be absorbed. But to maintain good health, does it have to be absorbed? And the answer is no, it does not. Some of it has to be, but not all of it. And what about gut function, GI function? Does it have to be absorbed? The answer is no. There's a lot of effects of gut inside the intestine, especially on health. This is a summary of a lot of data here looking at sulfates versus inorganics and the hydroxys. I've combined all the data here. And it's usually, and these studies are feeding multiple trace minerals: copper, zinc, manganese. And there's 5 different studies here. If we look at NDF digestibility, in almost every study, the sulfate was significantly or almost significantly lower, caused lower fiber digestion. Dry matter digestibility was also down in most studies with sulfate, largely because of the drop in NDF digestion. This is likely, I think it's the sulfate is inhibiting rather than the organics and hydroxy stimulating. I think is an inhibition. And I think it's probably mostly due to copper, but I don't know that for sure. So just be aware that feeding high amounts of sulfates might affect energy availability of these diets. Okay, this is a study Matt did again several years ago, or not, I guess several, but a few years ago, where he fed organic zinc, inorganic zinc, same concentrations. And he collected fecal samples, and he did this. I don't understand all this molecular biology stuff, but he did these things looking at for certain species of bacteria. And you identify a gazillion different bacteria. And what he found is that the pathogen associated with digital dermatitis, and it's a trichomonas, I think, when we fed the organic zinc, the concentration of that pathogen in the feces was lower. And so this is suggesting to us that the form of mineral that gets to the intestine is going to affect the bacterial population in that intestine, and that can have effects on the health. The gut is an extremely important immune organ. It can affect immunity, not because of effects on neutrophil and lymphocytes, but it might be an effect on the gut. So and this is a very active area of research now, is looking at how minerals affect the microbiome in the rumen and in the intestine. So this would be totally independent of absorption. So to wrap up here, remember the factorial approach only fits 50% of the population. And if you increase it 10 to 20% above the NRC mean, you're going to get about 97% of the population. So feed extra 10 to 20%. We're getting better on absorption coefficients, accounting for more sources of variation, but there's still a lot of constants, which, you know, you're going to argue why, even if everything is the constant, why don't we just use diet concentrations? Well, that's a legitimate point, but it's at least some feeds will have different ACs. The supplemental sources of mineral will have a different AC than corn or soy. There's a ton of interactions, and this is diet and the cow. You know, the status of the cow affects absorption. Cows in generally poor status, deficient animals tend to absorb more efficiently than cows in excess. Antagonists will affect different sources of minerals differently. A big practical thing here is the magnesium source. The supplemental source of magnesium have extremely different availability coefficients than 2001. This was in 2001, they did not have enough data to do it correctly. And so they grossly overestimated the availability. So if you're feeding a lot of supplemental magnesium because of low basal concentrations, you need to feed a lot just because it's so poorly absorbed. For trace minerals, these are still poorly defined, but I think they are better than just using concentrations because there are at least some variation accounted for. Copper sulfate has a different absorption coefficient than corn. So that's going in the right direction, but we still have a very, very long way to go on this. And then lastly, this is the new, I'm going to say the new frontier in mineral research is looking at the effect of minerals on gut microbiome. So just because something isn't absorbed doesn't mean it won't have some effect on that animal, either positive or negative. And with that, I think I stayed pretty close to be on time. So thank you for your attention. And I'll turn it back to whoever is moderating.
All right, thank you, Bill. Before we get started answering questions, we'd like to share a brief video, and then we'll be right back to answer the questions submitted during today's presentation.
Organic trace minerals come in many types and formulations, leading to confusion about chemistry, terminology, and methodologies. With Balchem's Keysure line of chelated minerals, we provide superior performance and exceptional value by keeping it simple. Binding minerals to the highest quality plant protein-derived amino acids and peptides in our world-class production facilities, using a true chelation process pioneered by Balchem and trusted in both the human and animal arenas for nearly 60 years. The Keysure line delivers proven and consistent bioavailability to maximize performance, and a no-frills pricing approach for greater profitability. Visit balchemanh.com to see how Keysure chelated minerals are your link to superior performance and exceptional value.
As a reminder, you can still submit questions to the questions pane on the attendee control panel. Dr. Weiss, your first question is, how can I assess magnesium bioavailability in the field?
One test in the field is the vinegar test, and Jesse Goff has procedures written on that. I don't remember exactly how to do it, but it's a pH, putting Magox in vinegar and looking at pH change. I'm not as big a fan of this as he is. I think it lacks sensitivity, and it doesn't give you a number. It's just going to say this is good or this is higher than this. If you're really concerned, I think an application would be, or an approach would be, you feed your diet and you collect some urine samples. And the first thing would be just to have it measure magnesium. If there's magnesium in the urine, that's telling you they're absorbing more than they need, because the cow absorbs magnesium and then it urinates out the excess. So if you've got magnesium in the urine, it's probably saying you've got enough. But you can quantify this by you collect urine samples from several cows and have a lab measure urine, magnesium, and creatinine. And there's equations. I don't have them memorized, but there's equations. You look at that ratio and it's going to tell you the apparent absorption is probably this. So we can actually measure that in the field with urine samples.
All right, our next question comes from Glenn from Wisconsin. What accounts for the large differences among Magox sources?
Well, Magox is not a mined mineral. It's a manufactured. I don't know what the starting product is. I used to know, but they take this product and they cook it at very, very high temperatures, 1,000 degrees. And that's a process called calcination. And if they cook it for too hot or too long, you get very poor availability. Or if they cook it at too low and too short, you get poor availability. So it's the temperature of the calcination. You can tell a little bit by color. If it's got a lot of burnt dark colors, it's been overcooked, but a lot of stuff looks fine and still not good. So calcination and obviously particle size. Magnesium has to be soluble to be absorbed, and it has to be solubilized in the rumen, which is a fairly neutral pH. So big particles are less soluble than little particles. So finer grind should increase availability as well. So particle size, which you can measure, and calcination, which you can't measure, are the two primary factors affecting absorption coefficients for Magox.
This is a similar question, maybe it's the same answer, but coming from Jim, would you comment on relative magnesium availability from dolomitic limestone?
The old data says it's not very good. There's been some newer processes, so I don't know. I've seen at least testimonial type things that it's better than we used to think, but the old data says it's very poor. So I'm just going to say, I'd say in general, I would probably discount that compared to high quality Magox. There's probably Magox that's no better than that, but a good Magox is likely better than dolomitic lime.
All right, the next one comes from Lucas. How do you pick a best mineral source when formulating a diet? For instance, magnesium sulfate or magnesium oxide? Would it be only based on price and availability?
For the macro minerals, I tend to price it on cost of available mineral. Sorry. So if if limestone 1 has an availability coefficient of 50 and limestone 2 is 40, and you do the math. But I base it on a price of available mineral, but I also base it on this intangible quality thing. If there's certain mag oxides out there, and I won't go into it, if you read my papers, you'll find what source we use, but it's consistently very good. So look for just quality in it, and because you don't want something that's good, this batch is good and the next batch isn't. So but I think availability, quality, and price for that. For trace minerals, it's still availability, but again, the inorganics will always be cheaper than the organics, always. That's just the nature of the beast. But we've seen enough things that there's something to a lot of these organics that they do something. The sulfates might be negative. So the organics, I'd base it on the literature, and the literature basically says diets with organics or these hydroxys, at least with a portion of the minerals as these, are worth more. So you can't just price it on availability coefficients for the trace minerals, because you look at, I'm making this number up, but if you feed half your diet as organic trace minerals, and you get a reduction in lameness by 10%, that has huge value. So for trace minerals, I base it very heavy on what the research says, and you try and give it value to these things in addition to absorption coefficient.
All right, thank you. Our next question comes from Fernando. How should you formulate minerals in the diet to reduce environmental pollution without losing high yields of production? What is the best way to do this?
Well, you want, good for the macro minerals, high availability coefficients mean you can feed less. So you would want to pick minerals or minerals that have high availability, or sources that have high availability coefficients. But when you really look at this, a lot, with a few exceptions, there's the availability coefficients vary, but the biggest impact you're going to have is how much total mineral is in the diet. So feed this, keep your overfeeding, and I'm a proponent of overfeeding. I don't think you should just feed to the requirement, but keep the overfeeding reasonable, and 10 or 20% to me is a reasonable overfeeding. Don't feed 50% or 100% over. Get your feeds analyzed, include the minerals in the basal ingredients in your formulation. Those are available to cows. And so those things, feed to reasonable overfeeding and high availability, especially for the macros.
All right, very well. Next question comes from Jose from Florida. Why would responses to sources of trace minerals, inorganics versus organics, vary with the type of diet? In your example, high forage versus high byproduct diets. If in general, trace minerals are absorbed by metal carrier proteins. So once these trace minerals get to the small intestine, the transport system should be the same, whether copper was originally in the sulfate form or associated with an organic compound.
Well, the transport is the same, but the mineral can be associated with something else that prevents it from being absorbed. Take copper, for example. Molybdenum and sulfur does not antagonize copper in a pig. It antagonizes it in a rumen, even though the transport is the same. So you get these compounds or the substances, I don't know if they're compounds, forming likely mostly in the rumen. That means that mineral, when it gets to the binding sites, to the absorption sites, is not available. One potential thing is in non-ruminants fiber. These fiber tends to be negatively charged. Trace metals are positively charged. You get these associations so that the mineral isn't soluble in the small intestine. It's bound to these fiber particles. So a lot of it is I'm going to say the form of mineral that actually gets to the small intestine. And that's where these antagonists come in, and where the source of the mineral affects it. So if the mineral soluble in the intestine and available, it doesn't matter. Well, I'm going to back up a minute. It mostly doesn't matter. But there's also data, and this is with pigs, or actually with cells, pig cells, showing that some of these transporters in the intestine actually absorb they don't absorb the metal, they absorb the complex. In this case, it was zinc methionine and zinc glycinate, I think. And we always thought that it was just the metal they were absorbing. But anyway, this cell culture data saying that in some situations, it's actually absorbing the complex. And that complex, once in the cell, is handled differently than the bare metal. So it has to do with the form or the association of the mineral with other compounds in the intestine or in the digesta, and then it might be the form it is absorbed in may matter more than we thought.
All right, very well. Jim is asking, do you believe the ratio of potassium to magnesium is a significant metric in lactating rations over and above the concentration of each individual mineral?
Now, I'm not a big fan of ratios, because both the numerator, you can change a ratio by changing the numerator or the denominator, and those should have very different effects. We know high K means you have to feed more magnesium. We know that, but I don't know if it's a certain ratio. We have equations too. So I'd say, you feed, if the way I do typical diets is, for lactating cows, is I decide, do I want to supplement K for added milk fat? If I don't, then our diets are going to be 1.4% K, typically 1.2, 1.4% K. I use this equation we have, and I've come up with the absorption coefficient for magnesium. If I want to supplement K and get these diet Ks up to 2% or so, 2.5%, for milk fat, then I again use this equation. The ratio is different. So I'd say those equations I showed you are the better approach than a ratio. But realize that as K goes up, you always have to feed more magnesium. The antagonism of magnesium with potassium starts below the potassium requirement. So you could feed a diet that's deficient in potassium, and it will still antagonize magnesium absorption.
All right, next question comes from Bill. Why do you think Moninsen has such an apparent effect on magnesium absorption based on magnesium source?
Well, it likely has a lot to do with potassium. And then the source one, like I said, that was we actually thought we'd get our hypothesis was exactly opposite of what we found. Because we know magnesium sulfate is more soluble in the rumen. Solubility drives absorption. And so we thought with Menensin is likely again this potassium effect, because to absorb magnesium in the rumen, K is involved, and K is also affects Menensin affects K. So this high sulfur thing is, like I said, I think if I staying around, I do this experiment, but I don't think it's magnesium sulfate. I think I could have got the same thing if I would have fed Magox and sodium sulfate, just elevate the sulfur. And again, I think it has to do with potassium interactions now with sulfur. There's other people, especially with sheep, have shown with Rumensin, Magox absorption is increased. Magnesium absorption from Magox is increased. That's been shown with sheep and feedlot cattle. So that was kind of expected, but this high sulfur thing was not. And again, I think it's not a mag sulfate thing. I think it's a sulfate thing.
All right, Mike from Wisconsin is asking, does NRC values have a 10 or 20% over requirement? And do you add to these base values?
In theory, NRC is averaged. There's no safety factor whatsoever. Some averages are better than other averages. Some averages might be 2 studies, but the NRC numbers would fit the average cow, at least, again, realizing the limitation of the data, but there is no safety factor in NRC.
Juan is asking, what is the best form of potassium in case of heat stress?
Well, you might get different answers, but if for heat stress, I think K chloride or K carbonate. K carbonate is probably a little better because of some buffering issues. But it's, in my opinion, one of the biggest reasons you should feed high K in heat stress is not to cover the sweat loss, which is there, but I don't think that's that big. But one thing potassium does is it makes cows pee a lot. They urinate a lot. And if they urinate a lot, that means they have to drink a lot. And it's a heat flux. You drink cold water, you urinate out hot water. So you can move a lot of water, a lot of heat out of a cow by really stimulating urination. And again, potassium is very, very good at doing it. Sodium is too, but potassium is really good at that. And to increase urination, it doesn't matter. The source does not matter. K carbonate has the benefits of higher milk fat, etc. K chloride, you don't usually see that. So I'd say for heat stress, if all you really want is the heat stress, and because of cost, I'd probably go with K chloride, but realize K carbonate has some added benefits on milk fat and rumen buffering.
Dr. Weiss, I see that we're at the top of the hour right now, but we have a lot of questions. In fact, we're not going to get to all of them today. Just wondering if you have a few more minutes for a few more questions.
Yep. Yeah, I can take a few more minutes.
All right, very well. Ruby is asking, does ration software count in the magnesium availability in this CNCPS model?
I'm going to have to say I don't know. My guess is probably not. I'm not aware of too many models that incorporate antagonism, and they need to. And we've gotten much better on this. So you'd have to check with someone at Cornell or read the book, but I doubt it does. NRC does not. Spartan does not. So I doubt it does, but there's equations that could be incorporated into it. Or you can incorporate, do the calculations yourself. But my guess is it does not. But if someone knows, please correct me.
Very well. Next one comes from Michael. What are your views on importance of calcium bioavailability, and what is the best methods for measuring availability?
Well, for a lactating cow, within reason, I'm not going to get too excited about calcium availability because limestone's cheap, and you can feed a little bit extra. Dry cows and fresh cows, it's a different situation. But I don't get too excited about it. You don't want something so poor where you have to feed a bunch of it and it's inert and takes up space. We don't have a good way to measure availability of calcium. Because we can measure fecal calcium, but calcium absorption is regulated. And so you feed a whole high calcium diets, apparent absorption is going to be low. You feed low calcium diets, apparent absorption is going to be high. So I really don't think there's a way to assess actual availability. In the past, and I don't know if anybody even does this anymore, there was this pH for limestone anyway, looking at how the limestone would affect pH in a lab, and that had to do with then if it really altered the pH, it was an active limestone and was a better maybe buffer. But I think on just bioavailability of calcium, I don't know of a field test, and even measuring it in a research situation is very poor or very difficult. But again, I think if you just buy good limestone, good particle size, you probably are going to be okay for lactating cows.
All right, thank you. Two more. Because of antagonism, should I alter trace mineral supplementation when feeding sulfate-based anionic salts to pre-fresh cows?
That's a good question, and we know that if you're using anionic salts and sulfates, we know you're going to be getting up to 0.4% sulfur. And at 0.4 sulfur, I guarantee you are reduced copper absorption, you have reduced selenium absorption. I guarantee it. The question is does it matter for 2 or 3 weeks? And for selenium, there actually was a study quite a while ago where they had the pre-fresh was only 2 weeks, and it didn't. And they were looking at selenium status of the cow and of the newborn calf, and it didn't. The 2-week high sulfur diet did not affect measures of selenium status. So I think, and for copper, we feed so much copper, and livers and most of these cows have more than adequate copper. So even if you reduce copper absorption by 50% for 3 weeks, I don't think it's a big deal. If you were feeding anionic salts the entire dry period, that's a different issue. Then I would be concerned, especially with selenium. But for a 2 or 3 week pre-fresh at 0.4 sulfur, make sure that all the cows are fed adequate all the time, but I don't think I'd worry too much about increasing concentrations for that short pre-fresh period. You might think about for selenium, and I do this anyway, but you might think about putting at least half or so, a goodly portion of the selenium from yeast rather than all selenite if you're feeding the sulfate.
All right, and I think this is a good one to end on. Having served on the last 2 dairy NRC committees, what are the top 2 to 3 research studies that are needed relative to mineral requirements in dairy cattle?
Well, I said I think we're getting on the macros. I think we're getting pretty good on those, and I think the requirements, and they if you look over time, they're pretty much on the tweaking side. Trace minerals is more difficult. I'm just going to say we clearly need, if we're going to go to absorbed minerals, which we need studies looking at availability from ingredients, not supplements. Manganese concentrations of ingredients vary widely. Is the availability coefficients of corn different from alfalfa or whatever? We have no idea, none whatsoever. So a few studies like that would be useful. And then the problem with the NRC approach is it's this factorial thing. And you look at, okay, we're replacing everything that the cow loses every day. But is that really, if we're having these effects in the gut, if you feed just to meet the requirement, is that enough to see these microbiome effects? So there's a lot we still don't know about non-factorial effects of minerals. This effects on fiber digestion. What are these different minerals doing for the rumen? We have, with molecular biology techniques now, we can do so much more than we could 10 or 20 years ago. And I know people are looking at this. So I think to look at things other than milk, repro, or fetal growth, look at what else do minerals do that we do not account for in the factorial system.
All right. Thank you, Bill, and thank you everyone for attending today's webinar. If you have additional questions, please submit them to anh.marketing@balchem.com, and we'll forward the responses to you along with the unanswered questions from today's session. We have 2 additional webinars coming in March. Our next webinar will be targeted toward our companion animal audience and will feature TED Talk style presentations from 3 grad students in Dr. Greg Aldrich's successful pet food program at K-State University. The second webinar on March 23rd will be presented by Dr. Emmanuel Borca, where he will review the latest updates from the USDA on the status of an African swine fever vaccine. Our next webinar for our ruminant audience will be on April 6th. Dr. Mike McCluskey, co-founder of Fairlife LLC and co-founder and CEO of Select Milk Producers, will join us to share some practical on-farm ways to begin moving toward net zero carbon emissions. Visit balchemanh.com/real science for more details and to register. Balchem's podcast series continues to offer a deeper dive into our webinar topics. We now have 9 episodes on YouTube, your favorite podcast platform, and also at balchemanh.com/podcast. We go behind the scenes and hear the conversations that take place over a few drinks with friends. Search for Real Science Exchange on your favorite podcast platform and be sure to subscribe. On behalf of Balchem and Dr. Weiss, thank you for joining us today.
Thank you.